Hello, everybody, and welcome to the 31st episode of the Hyperthesis podcast. My name's Liam.
I'm Patrick.
I'm Pheely.
All right, it's good to be back. Today we're going to talk about some interesting topic, the heat death of the universe, which is, I like throwing that word around, but in all reality, I don't even know what they mean. So I'm excited to hear about that from Pheely later. But first, does anyone have any interesting news? If no one does, I have some stuff to talk about, or complain about, I guess.
Just one thing I want to say quickly. I read this yesterday, and scientists have shown that the Earth's core may have either slowed down or started spinning the other way. Really cool news. Have to look into it more, but just wanted to mention it.
So what does that mean? Because, doesn't the Earth's core basically, it creates this big magnetic field that protects us from a lot of radiation, right? Maybe?
Right. So the Earth has an outer core and an inner core. So the outer core is the one that produces that magnetic field, which we'll get into in the story more. Spoilers. Whereas the inner core, it's essentially this solid piece of iron and nickel. And it's solid because of the pressure. But part of the core, it's either the outer or inner core, has actually slowed down or reversed direction in the way it rotates. So the inner core actually spins faster than the rotation of the Earth, whereas the outer core flip-flops a lot because it's very hot and turbulent, and a lot of strange stuff happens in there.
I'd originally guessed that they were kind of, I would have guessed that they just spun one way and stayed that way for a long, long time. I guess there'd be turbulence and stuff going on, but the overall motion I would have guessed is just one direction. So yeah, I guess if the inside core is spinning in the opposite direction, maybe friction caused it to turn around or something. I say friction loosely.
Yeah, I think it's still being highly researched because we can't really dig down there and see what's happening. But yeah, it's interesting to see what's happening with and what might be causing this, because apparently this type of action happens every once in a while, so it kind of oscillates back and forth in how it spins and in the direction it spins, and they're still trying to figure out the mechanism behind that, from what I understand.
And it's really difficult to dig down into the core of the Earth. It's just guesses, right? Like it's too hard for any type of equipment to go down and measure it. And so we only have indirect investigation. Even though we can go to the moon, we can send probes to Mars, we just can't seem to get down to the surface, to the core of the Earth. We can barely crack the crust, barely. The deepest hole just doesn't even go down to the, doesn't even penetrate to the crust, right? But we have all these theories about tectonic plates and how Earth core is formulated, or different layers of Earth core, which is fascinating from the limited knowledge or limited instrumentation that we can do. And one thing I want to put on this disclaimer is you might notice my voice has become a little bit raspy and unbecoming because at the time recording was the day after the Super Bowl, and the Super Bowl has been tormenting me last night. I had to scream at the TV, and so there we go.
I will also put out a disclaimer that my voice will also be raspy, not because of screaming at the TV, but because of a common cold. Thankfully, not COVID.
In the past, I was going to say, in the past, I've had a whole bunch of colds, and I probably should have warned people about my voice. I never did, though.
But yeah, this is very interesting news about the inner core and its changes and how little we know about it and understand it. I think we will actually have to do an episode on this. I'm in the same department as a lot of geologists, so maybe we can get one on to talk about the core of the Earth and how we make those measurements.
Go add it to the list. The massive list of things we want to talk about. I want to complain today. It's one of those complaints where I signed up for it and now I'm complaining about it, but I have a comprehensive PhD exam in about a week that I've been studying for. So that's been the bane of my existence recently. So a lot of universities, it's different everywhere you go, but a lot of them have this thing where in the first or second year of your PhD, you have to write this big exam. And sometimes it's like a big exam on all of the knowledge you learned during your undergrad, or sometimes you get presented a new project and you have to research it and talk about it. Mine is kind of, I chose with kind of the supervision of my committee a few textbooks and some chapters from them that I have to learn about. And then I can get, it's like an oral test. So I go in and they basically just, well, I don't want to say berate you, but they just ask you questions for 2 to 3 hours straight. And at the beginning, I have to give a little 20-minute research presentation.
And comprehensive exam is a clear distinction between PhD student and PhD candidate. I think we should explain a little bit in more detail, because when you start in your PhD, you are a PhD student. Great. But once you pass your comprehensive exam, you are the PhD candidate, because, they try to prove like, oh, you have the capability, at least, they believe you have potential to get your PhD. So that's you're a candidate now. So sometimes when you see these, some people use this interchangeably, but there is a slight difference.
Yeah, no one ever told me that for a long time. So on my resume for the last 2 years, it said PhD candidate, but I didn't know the difference until a few months ago.
You fake.
Yeah, I have to pass this thing before I can use that.
I will just say it's also called a candidacy exam as well as a comprehensive exam. I think it just depends your field and who your supervisors are.
Some universities don't even do them, and some of them do, and they're like, it's so situational depending on your department and university. And
it used to be also like you do some place in the past used to do it after the first year, and the first year in your PhD you just study, you don't do research, you just study for the comprehensive exam. And it turned out that it's not the most efficient use of your time, right? That's why a lot of places change to a more like either like a presentation format or some kind of auto test that doesn't require you, like, it's not as intimidating. It's like, oh, you have to be tested on every single subject, or like that's why it's comprehensive. And some people are not good at writing exams. And are we gonna say all PhD must be good exam takers? I mean, there are a lot. Like in physics, they're experimentalists. They're almost like the astronomer. They're good like data scientists basically, and statistician, almost all observationalist. And they're not exactly, some of them are not great exam takers. Doesn't mean they're not capable of doing a PhD or be an expert in their own field.
Well, usually by the time you're that far into a PhD, like, even if you're not great at exams, you're still okay at them because you passed through like a bachelor degree and a master's maybe. And if you didn't do a master's, you've already done a few years of your PhD. So like, but I see what you mean, right? Like, it's kind of, I don't know. They're like anything. There's benefits to them and there's also downsides.
It is a bit different than like an exam that you sit down and take, though, because instead of like judging your knowledge on a certain area, like, for example, with calculus, making sure that you can do derivatives and integrals and can you figure out the weird tricks that we use for some of them. It more so just, I guess, proves that you have a good understanding of the background knowledge and science that happens. At least for the ones that I've experienced and witnessed, it's more of a tell us everything you know. We're going to push you to your limit of what you know. So it's less, okay, you need to have all of this very you still need to have this very specific knowledge, but it's different than an exam in that tests your knowledge and it's okay not to know things.
Yeah, from people I know who've taken them, they kind of, they don't expect you to have the perfect answer for everything, at least the one I'm doing, where I'm kind of just like standing in a room with some examiners and they ask me questions and I just kind of like wing it on a chalkboard. But they expect you to kind of like be able to set up the problem and understand what's going on. And if you can solve it, excellent. And if you can almost solve it, that's good enough, I think, is kind of the idea. I mean, depends who your examiners are and what questions they ask and all that. Like, it's so situational.
Well, and also it's like how we also test our students too, right? Like it's not about arriving at the answer, it's about the rationale behind your methodology. And having a good scientific understanding or scientific rationale is really important, like how you approach a problem, how you try to solve it in a physics way. And so there should be some kind of a standardized way to think about it, which to me makes a lot of sense. Right, like you should be able to think like a physicist if you want to be a physicist, and that also comes into it. A lot of people who has a different background, maybe computer science or engineering, who come into physics, they got challenged on that a lot. Like, oh, do you know this theory? Do you really know your quantum mechanics? You understand why these theories are important, or like the rationale behind these theories? Because you can't. To me, is you can't be calling yourself like a doctor of physics and not knowing quantum mechanics, or at least the postulates or the principles behind them, and in at least high understanding than undergraduate level. You have to have this kind of like mature development of these kind of like advanced theories at least.
Yeah.
Saying that, I'm still haven't done my candidacy, so I hope soon. So.
Yeah, I mean, as long as you get it out of the way at some point, right? I don't think it really matters when. They just tend to all do them at once. So at McMaster, they do them all in your second year of your PhD in physics for some reason, instead of your first year.
Yeah, I think it's pretty standard within like 20 or 24 months that you do your candidacy. But I also know people that did their candidacy and then a couple months later did their final defense.
Mm-hmm.
So it's kind of individualized, but generally it's within the first 2 years.
So I have 2 textbooks I've been studying. One's on, I challenged myself with this, which is maybe a mistake. I decided to, what you usually do is you choose chapters from textbooks which you already know. So you if you took a class on quantum mechanics in grad school, then you choose like the textbook you use for that class and get tested on that knowledge, which is stuff you've already seen. But I chose an entire textbook which is on quantum field theory, which I don't even directly use in my research at the moment. So we'll see how that goes. And then my other textbook's on Bose-Einstein condensates, which is, I actually know that stuff pretty well, but I'm learning a ton of stuff about it. I don't know how I never asked this question, but if you think of like a phase space diagram, right? Like you think of like, you have something and under a certain pressure and temperature, it can change between a liquid and a gas and a solid. It's like, why is it that in Bose-Einstein condensates, there are these ultra cold gases? You can make them as cold as nanokelvin. They're very cold, but why is it they're a gas and they don't crystallize? And somehow that's like a super simple question I never even thought about, because you just get presented with this stuff as an undergrad and you're like, yep, these things exist. And sometimes you're astute and you pay attention and you ask these questions, but somehow that one just never occurred to me. So I learned why Bose-Einstein condensation it's a metastable kind of thing. It's a gas, but under certain conditions it'll all crystallize into a solid because it's very low temperature.
Well, we will learn in the main topic today. I will claim that everything is metastable.
Oh, okay.
Whoa.
Everything is phase transitions and everything is metastable.
Not everything is phase transition.
I like to think it is. Like not anything. Yeah, anyway, I won't get into that. But
they can have phase transition, but not everything is phase transition.
Okay. All right, but maybe we should get on to that, the main topic today. So Pheely has been thinking about this a little bit recently, and he wanted to talk about it. So I don't know what to expect, but I'm excited.
Well, I've been in deep thoughts for a while. I felt like when I went home and shut off my brain and kind of like let things go, and technically, in the way I see it was like I lubricate my mind by not thinking a little bit, just and thinking about other things about that are not as profound. And now I'm back about in my deep thoughts about profound stuff and about like the implications and meaning of things like in physics and also in other part like philosophy and other things. And one thing that strikes me is I don't know who mentioned the heat death of the universe and the eventuality or the apocalypses. And in also you can think about it in the biblical sense or like in a kind of religious sense or more like a realistic sense or like a physical realm that's like the world's ending or the universe is ending. And also, that really what I want to talk about is more like a physics sense, in a statistical physics sense almost. And it has a unique perspective, and that is a little bit cynical. It's like a little bit like pessimistic that, it's going to come to an end. There's something eventual heat death of the universe that is unavoidable. So we're going to be talking about that a bit, and why, and what's the basis behind it, what's the mechanism behind it, and why science kind of produced such thing, and why is it natural. There's a lot of questions that you can start asking about it. So Liam, we were talking before about metastability,
Yes, yes.
and it's good to make a distinction between unstable, stable, and metastable. And if you look at I don't know how physicsy I should be about this, but if you look at what we call free energy, or let's not talk
I
about free
like
energy.
the
Let's say,
example where you have a ball on a hill or something like that. That's the way I think of it, but maybe that's too simplified.
yeah, in a way, right? If the ball is on the top of the hill, that's an unstable phase, because you tip it a little bit, it's gonna go downhill. It's gonna change. But what would you say something like a stable phase? Maybe a ball in
The
like
bottom
a
of the hill, like,
cavity.
right, like,
Yeah, the bottom,
yeah,
like the yeah. If you think about parabola, right? If the coefficient is a positive, so it's a what's called concave parabola, and you're gonna have kind of like a little pocket, basically. If a ball exists inside a well, I think that's a
yeah,
good word, a well. You use that a lot in physics. And a well that seems stable, right? Like you move a little bit, it wants to come back to the same state. Like, great, that sounds stable. And what is the metastable? Well, imagine you have you in a stable well, but that's relative, right? Maybe there's a better well at lower energy. So a deeper well, basically. So once you have enough energy to go past the barrier of your well that you're comfortable with, and you go into a deeper well, that to me, well, is that more stable? Well, that's also a stable phase, right? It looks stable. I mean, if there was a ball in it and it doesn't move, or it tries to goes back. So what do you call that intermediate well? So that's, in a way, this is a really reductive description of metastability, I guess. But here it is. Then do you have, imagine you have two wells, right? The shallow well and a deep well. So the deep well is more stable. So, well, but you can be metastable without, you can be metastable for a long time without going to a stable phase.
yeah. It's like it's stable, but if you give it enough push, it'll become unstable, I guess.
For example, glass. Right? Glass is amorphous phase, is a metastable phase, or even diamond. Or diamond, in a way, is in this kind of metastable ish, right? Because diamond form in a very, very high pressure, and that's the stable phase, you would call. But when you take it out onto the air, that very low pressure compared to where it's likely to be. So it wants to become graphite, because has a lower energy phase. So in a way, diamond is at the metastable phase, where it's like, well, it wants to be diamond. You already crossed that barrier, but it can be metastable for a long time. That you also see in glass window, the top would deteriorate and gets thinner, because it's metastable. It doesn't want to be glass.
I don't know what you were about to say, Patrick. If you were thinking the same thing I was, were you thinking of that water bottle in the freezer experiment? Yeah, you were. I could read your mind from across Zoom. Uh, my favorite. There's a really simple example of metastability in you take water, you put it in your freezer, and you get it to just the perfect temperature. I think, Pheely, you might know more about this. It's like super cooled water where it's at this temperature where it should be frozen, but it's not quite there yet. And then you take the water bottle out, it's still water, and then you kind of smack it on the table. And by adding that extra kind of kinetic energy to this super cooled water, the entire thing will suddenly change state, because the super cooled water was a metastable state. By adding the energy, you pushed it to its new like ice state, and the whole thing will suddenly freeze. You can Google that or YouTube it, and it's a really neat little experiment you can do at home.
Well, there's a question: can water go below 0 degrees Celsius? Right? Like, and people are like, oh no, because you get zero and it's crystallized and it becomes ice. So like, well, but if you do it carefully, there's a way through thermodynamics that are like, it's just simple experiment. People try to figure out by trial and error the heuristic process that, if you put in this for 2-3 hours in this temperature, you control it very carefully. The process at which crystals are formed, I think what we call it nucleation. We try to reduce that so it doesn't happen, it doesn't crystallize. So the water goes below 0 degrees Celsius and it doesn't freeze, it becomes liquid. But the phase, the state that it doesn't want to be liquid, right? It have this like a, imagine like an angry baby or something. They don't want to be inside the house, they want to be outside the house, and they really really want to get out of the house, and you're like, no, we're gonna keep you in the house, all right? Like, we put doors in there, and and it's like, okay, but it doesn't mean that the baby doesn't want to go out and play. So what happens when you poke a hole through the door, right? It's gonna run out and play. So it's like that. So the water wants to be solid, but it was forced to be liquid. Basically, that's what supercool water is. And any perturbation to that state by tapping it, cracking it, it would introduce shockwave into that and introduce like forcing it to basically like tipping the ball that's on the top of the hill, right? Or like on the side of the hill to go down.
Yeah, and that's what I learned about this Bose-Einstein condensate, this ultra cold gas that I study, is that you can mess around, you can get a really dilute gas, so a very, very low density gas, and you can essentially there's these things called one body, two body interactions, and I won't get into it, but because for the sake of the topic we're supposed to be talking about right now, but you can, if you increase the average distance between two random particles in your gas to be really large, you can still do it such that you reach a kind of like kinetic equilibrium. But if you increase the average distance between the three body interactions, so the really, really, to be really, really big compared to that of two body interactions, you can actually reach this metastable state where it doesn't crystallize, although it wants to. But yeah, I won't go into that. I just thought it was interesting that no one ever mentioned that to me. Ever learning about Bose-Einstein condensates and reading through this deep into this book, it was just like a little side comment somewhere in the book, and I was like, huh? Anyway.
So you mentioned something, Pheely, that I just want to, I guess, put a pin in and talk about for a second, and that's nucleation. So, for example, how water is able to form in this, or ice is able to form in the supercooled liquid is through tapping it or changing it in some way such that nucleation occurs. So you get one little ice crystal, and then suddenly you have a whole bottle filled with ice. So the same thing happens, for example, with clouds. So clouds can actually form without the presence of dust because water doesn't have enough energy essentially to clump when it's in a vapor. But when you put a little bit of dust in there as like the nucleus for a future raindrop, what will happen is that water will collect on the surface of the dust, and suddenly it's easy for the water vapor to condense onto the surface of this dust. And this happens for many millions and billions and trillions of dust particles, which will form clouds. But nucleation itself is the process where you essentially have this seed for some sort of state change or phase change.
So, what does all this have to do with the heat death of the universe? What does metastability have to do with this?
Well, the key word that I think we haven't mentioned is entropy, and we'll touch on the entropy. Is to me is one of the most profound concept. It's, well, I'm gonna say it here. It's better. I think it's more profound than quantum mechanics, more profound than relativity, it's more profound than string theory.
Yeah, I can agree with that. I think entropy is pretty much everything. It's a hard topic because not a lot of people truly understand it, even like physicists.
For example, right? If quantum mechanics deals things at pretty small scale really well. That's why people try to work it with quantum gravity. It's not successfully yet, right? But there are places where classical mechanics dominates. There are places where relativistic stuff dominates in GR, in like celestial mechanics, all these black holes and stuff. But none of those theory can break the law of thermodynamics. They can't get away from entropy in any length scale, any point in any theory in physics. They're all governed by thermodynamics and this kind of entropy. And people kind of push it away, put entropy and thermo and statistical mechanics on the side in the little box, like it describes this kind of heat engine and this system. But no, it's described like your entire universe, basically. How things are kind of formed, and you could make an argument that entropy gives rise to time itself, but that's another story. But okay, let's go back. Let's trace back a bit about metastability. How do you know your phase is actually the lowest energy? How do you know it's the most stable thing? If you say, oh, my system is in a stable phase, well, if I give it an infinite time, would it still be in that state? That's the thing, right? You as a material or an object or a matter can be in metastability for a very long time. Glass can stay glass for a very long time, but you give them thousands of years, it breaks down to this silica, right? So, well, then we know, oh, that's metastable. It lasts for a long time. So, well, diamonds, people think it lasts forever, but if you put it in the air, that's or like leave it for a very, very, very long time, maybe it becomes something else. Maybe there are other phases that have lower energy. And to me, it's like, well, is everything metastable then? If there is like the end of the universe, basically, where everything kind of dissolves to be the most stable state, it is. But I have to be careful about that because there's something what we call entropy. Entropy has many representation per se that some people say is information or self-information of a system, or some people say it's disorder. Some people say it's ignorance of the system or uncertainties of the system. There are many views that you can look it up. Like I think chemistry has a point of view. Clausius has a point of view on when they start. There's some irreversibility that come from entropy that defines entropy. That from heat engine. When you try to make first engine, steam engine, or whatever, right? Or even the heat engine with heat bath, that it is quantity that's always increased if you don't put work into the system, isolate the system. All interaction seem to increase this thing called entropy. I think it was defined as change of heat over temperature or something like that in Clausius' definition. And then Gibbs and Helmholtz and Kelvin and those like fathers of thermodynamics came along and have different definition of things and redefine in terms of probability distribution and how to formally deal with entropy and how to see it as like statistical thing. And then came along information theory, which are more like give rise to this explanation that entropy is about self-information, about ignorance in the system. So entropy is very complicated, and the fact that entropy kind of increase all the time is that law of thermodynamics, right? Like entropy always increases if you don't put work into it in any system. So the phases, the universe increases entropy. Like the entropy is the total entropy of the universe increases and keep increasing it. And in any system, isolated system, right? You reach what people call like the stable phase or like the most stable phase when the entropy is maximum. So it had the maximum entropy, and once it reached maximum entropy without any work, you don't put any, you don't disturb it, keep it isolated. Nothing else can happen inside that because it reached the absolute maximum entropy, the maximum disorder, or you'd say, or a maximum irreversibility it can have, maximum self-information that it can have.
Yeah, I think all these different ways people view entropy, I think mathematically it just comes down to like entropy is like kind of the total possible number of configurations of your states, or you kind of sum together all possible. Like if you have particle A and B, that's one state, but then you swap their locations, that's another state. And now you do that for like millions and billions of different states, and you get this entropy number, right? Something like that. they call it micro. It's like your total number of microstates is what they say.
Yeah. Well, that's a part in that too. But in the early day of entropy, it wasn't like that, right? It was like a change in heat. But that's like pretty old viewpoint.
Yeah, and the other thing too is that everything comes back, like you say, everything comes down to entropy. Like one of the most kind of fundamental, I don't want to say one of the most fundamental things in physics is that if you have some system, it wants to be in its minimal energy state. It will do things until it reaches its possible minimal energy that it can have. It doesn't, if you put this ball on top of a hill, it wants to roll down the hill because of gravity. It wants to decrease its potential energy and then hit the bottom of the hill and become motionless. You're minimizing your energy is synonymous with kind of maximizing your entropy. You can show that. I did it in one class at some point in my life, but they're the same thing basically.
Well, but I bet you never done this. Well, anyway, what you were talking about is so like it minimizing, extremizing action, right? Which is a term like Lagrangian. But anyways, like there's mechanics behind it. But I bet you never done entropy to information theory, and it's about what is self-information. If you had like something that's like a random variable, for example, or like a variable or a number, it's like intrinsically is there a self-information that random variable has. Let's say if like an event, let's say have a probability to happen, right? P, well, what can then that event has some kind of information by itself intrinsically. So it's like, well so information theory, to give a little background, is a theory, is a mathematical theory of communication. How information propagates on being communicated between events. It's almost like a little bit like relativity, but it's a more fundamental sense, and it is a very abstract fundamental sense. So if you have two events, which probability p and 1 minus p, right? Like think of it like a 2-bit, right? It's either happen on one happen or two happen.
Flipping a coin is a pretty good example. It's either one side or the other.
Yeah. But the thing is, if you think about that, if you think of entropy as ignorance or uncertainties, right? If you flip a coin and the coin turns out head, or that is certain now. So probability, if you think talking quantum term, collapse, right? And you know 100% certainty, so the uncertainty must be 0. But when is it that the entropy or uncertainty is maximum? Is when it's 50-50. Right? Because that's the most uncertain you could be. If you have two states, there's no reason, if it's isolated from everything else, there's no reason to think one state is more preferable than the other. That's I think, well, one of the assumption of the statistical mechanics.
I was about to bring that up. Is that's like one of the key assumptions, but I know
equal a priori probability.
I know someone who's doing research in that area actually, because it's this kind of fundamental assumption that each state is equally likely. But there's no I guess there's no, intuitively it makes sense, but there's no, I guess, mathematical reason why that must be the case.
Well, it actually does.
Well, it does because
it gives the most entropy.
It does because it gives us things that match the real world. But I guess
no.
Yeah.
I it's much more fundamental than that. No, I think that is BS. It's like it's matching the real world is a small part of it, and because I have not talked about the real world at all. I'm talking about like abstract entropy. There's nothing about probability that I was talking about has anything to do with the real world. I mean, you could have any kind of random variables in your head with certain probability of events, and that have no physicality at all. But if you had a distribution where the maximum entropy is when the probabilities are the most unsure, if you have, let's say, an event, the most unsure state is when all the events have the same probability, right? Like, how are you sure that other ones, one event would have more probability than the other, right? The most confused state you could be is when everything is equal.
Mm-hmm.
I think that's not an unreasonable assumption. I think that's a fundamental assumption that has nothing to do with the
Well, I
physical
mean,
world, and it doesn't match
it's
anything.
well, as far as I'm concerned,
It's a
yeah,
logical
it is. But as
assumption.
far as I'm concerned, if you make a logical assumption and it spits out something that doesn't make sense with the real world, then it's wrong.
Mm,
Like, but it's right. It turns out it's
mm.
super logical assumption. But yeah, I know someone who's researching that assumption in some sense. Why is it the case that that's true? And again, it's intuitively it makes perfect sense why it's true. But I guess if you think about it deeper, there's reasons to believe like why might it not be true, or what reasons make it true. I guess.
So we're looking at this, I guess, from a
Yeah,
theoretical perspective, but how does this relate to the heat death?
yeah. We're gonna keep coming back to that until we get there.
Yeah, I keep getting stopped, so we'll
Yeah,
get there. So I'm just trying to explain the concept of entropy. So if you think of a disorder and stuff, so things want to be actually at the maximum entropy when basically if you think of disorder, right? Things want to be at the most confused state. Sounds weird, right? But it's true. You can relax any system, any physical system, you relax it and you wait long enough, sufficiently long, and we just go to the most state that has the maximum entropy, and that is true. and and one could say it's like, oh, that's just time in the making, that's just the way the world works, and entropy will increase. Or you can also say like, oh, fundamentally things want to have highest entropy because that's the most ignorance that we could have about the system. So try to have go to that state of the basically where the system has the most uncertainty. Okay. Okay, I'm gonna re-terms everything, all these stuff that complicate. I just call it entropy, highest entropy for some reason, right? And and to the heat death of the universe, here's the punchline. You, our universe is an isolated system. Yes? Like, it's
is
an
it?
isolated
Do
system.
we
Just
do we know
if you
that?
accept that.
Okay.
If you accept that, we haven't done
Yeah.
evidence
Okay.
otherwise. We haven't found evidence otherwise that there are other dimension thing or like outside of the observable universe that add energy to it. We haven't found that evidence. Maybe there are. But if the universe is isolated, yes, is as time continue on, it would try to reach the state of maximum entropy. And once it reaches the state of maximum entropy, nothing can be done. There's no reaction that can happen. There's nothing that could happen because you are the most fundamental state, the groundest of ground state ever, right? Everything would turn to dust, and to the most, maybe protons would break down. Maybe everything would turn back into fluctuation of fields, right? But where because we are living in the metastable. And once we reach the most fundamental stable, where entropy is maximum, without work putting in the system, as we can see from smaller system, where if we isolate it, it would reach that final state and stay there. The only way to decrease entropy is to add work or energy from outside the system. So if your universe continuing to expand, like increase entropy, it would reach the maximum entropy possible from a system, which is a lot though. That's the thing, that's the scale that we don't talk about much yet. That like, well, we talk about, oh, the heat death is eventual. Yes, it's eventual, is maybe unavoidable, but it might take like billions and billions and billions of years to reach that point, right? It's not close. It's by any reach possible, like, or any idea, concept perceivable that's close, because like, even glass takes thousands of years to deteriorate. And you think, how much you think the universe would deteriorate to the most entropy state, right? So it takes a very long time, but the fact that entropy is always increasing is going to reach the maximum one day. Like, I mean, that just, to me, that's just mathematical truth in a
Yeah. So
way.
that assumes the universe doesn't really interact with anything, which again makes sense. I think that's a pretty decent assumption. But then I won't get into it, but you get all these like parallel universe theories, and are they isolated? Do they interact? I don't know. But yeah, it would take a super long time, because it's like, I think about black holes in general, and these really big black holes, they they could take like 10 to the 64 years to evaporate according to our current theory, and it's like that's a massive amount of time because that then all the other stuff in the universe has to happen. So it's so long that it's like insane to even try and comprehend how long it would take. But so what does this have to do with why is it called the heat death? I guess. Yeah, I'll let.
Well, I thought it was pretty self-explanatory. I mean, it's you ran the way I say it is like you ran out of heat. Everything that dissipates to nothing, and it will eventually happen. And I would like to mention a little bit on like the literature or the like what's it called entertainment literature to try to like now a lot of fantasy literature has come to like address a little bit of this that indirectly if you think about like you connect your universe to another universe, like you think of the Witcher series, right, by the conjunction of spheres, you have different universe have bridge between one another, or a lot of these parallel universe stories that that might be in a way one day if you find those it might be a solution to the heat death of the universe, because now you can take maybe the black holes do that, who knows, because like maybe now you can take energies out from outer place to increase your entropy. And about this heat death of the universe thing, is I think I explained it quite a bit now, but I want to point out the fundamental part on statistical mechanics and why I think this is quite important. I'm not sure if I talked about this on the podcast, but I surely talked about this to a few people. I'm not sure if I'm really right, but well, for now, who knows? Maybe in 10 years, my thoughts would change about this. Well, Liam, a question for you: what's the nature, fundamental nature of quantum mechanics represents? What does it tell us about the world or like the universe? Like in short, in like a couple words.
It tells us that you can't know anything exactly, for one thing.
Yeah, so it's about measurement. It's the nature of measurement, right? And to me, that's great. Okay, quantum mechanics describe nature of measurement, of all measurement possible. Sure. So what is in the same manner, what's the nature that general relativity or relativity describe?
Wait, so like what do you mean? So
yeah, what's the fundamental nature for general relativity?
That nothing go faster than the speed of light. Yeah.
Mm-hmm. To me, general relativity and kind of string theory is the nature of geometry, and how higher dimensional geometry manifests in lower dimension, maybe as gravity, as particles, as stuff. So it's to me that's the explanation of like intrinsic high dimensional geometry, right? Like because like measurement is real. Is real is how we make measurement, and geometry is something that's kind of objectively out there that being manifest into the physical world. So it's more like a kind of Plato view of the world. But anyways, like there are this theory of geometry, and classical mechanics kind of like a loose theory to explain mechanics in between. So, but what are statistical mechanics? It doesn't fit in the length scale because it's kind of an umbrella that overshadow everything, right? So to me, the statistical mechanics and especially entropy is a theory about the fundamental nature of counting. Because you can measure things, you can have geometry, but you also have numbers. How do you count? One of the first thing you do in stat mech or thermodynamics is like, well, you have 10 balls of different colors, and like how many configurations or like how many ways can you organize the ball? How many what's called multiplicities, right, of the system? Like, well, then you have to start counting, but you don't do that really in auto field in this kind of in this fundamental way, right? So it tells you a lot about how things are counted, how numbers actually work, and how the principle behind counting becomes entropy and becomes the dictates even time almost. Some people would say that because in quantum mechanics you kind of assume time as this, okay, there's a time going forward. GR is like, oh, it's a consequence of higher dimensional manifestation. But in in statistical mechanics, like, well, maybe there's a limit to counting, like all these very large number of probability or multiplicity that the universe can have a limit to, so, but we are not
Yeah,
there
so
yet.
it's like no matter what you think of entropy as, it comes down to counting things. I have this book back there called Statistical Mechanics for Babies. If you've seen those books before. And yeah, it's just like most of the book just talks about how you can count different ways, count different configurations and things like that. So
The reason I talk about the fundamental nature of things, like me, is directly linked to a lot like philosophy, like how you view the world as a physicist, right? I think the philosophy of science is really important, and people sometimes, I think, take things as like objective truths a lot, and as we can see, a lot of we are wrong most of the time in scientific history, and but it doesn't mean it's not valuable. There are, I think, a huge value in understanding our measurement, huge value in understanding how geometry manifests, or like what is geometry in the physical sense. And now that's kind of pushed aside as a much smaller field is the nature of counting and statistical physics, which fascinates me. That's why I'm keeping doing this. And I was a little confused when like, I was interested in quantum. GR was great, and so I was like, why am I doing stat mech? Right? It doesn't make that much sense when I first started. It sounds like this little small theory that's not as fundamental. It's very almost phenomenological when you see um, the experiment, or you see what's going on in the world. You start to create model to explain that. But then you go to deeper into statistical mechanics, that you can have very, very fundamental axioms or understanding of things on how you view the world. To me, when I came to the idea of the nature of counting, it blew my mind, because that maybe that's what it is, that that's what's missing, because counting is such a fundamental thing to human. We have base 10, because we have 10 digits. I mean, that's not an unreasonable assumption to have, right? Like that's like, well, what do we do first thing when you try to learn mathematics? We count. Yeah, 1, 2, 3, 4, 5. The nature of counting is closely related to human nature. That's why I'm stuck in this. Like, wow, I'm not exploring how we view the world by through measurement. I'm not viewing how we perceive abstractly geometry to the world. We are perceiving what's the most human thing we could do mathematically is to count. And it's why this is more explanation of my belief in my field, and why it's so crucial to understand these things, why it's such a vital understanding that we must have. Because, like I said, entropy governs all, right? All systems, and including the weird one we find, nothing breaks that. And get back to a little bit on the heat death of the universe, like it eventually gonna get there, but like Liam said, it might take like, in human sense, like an infinite amount of time.
yeah, and there are also all these other theories of how the universe will end, but we won't bring those up just because. Oh, Patrick.
I do just want to bring one up, just quickly, and it has to do with what we're talking about. So, from a particle physics point of view, we have what's known as the Higgs boson, which is an excitation of the Higgs field. So it's a particle that is produced by the Higgs field, and this Higgs field is all permeating. It's everywhere, and it's assumed to be what causes mass, or anything to have mass. So just quickly, it's thought that the Higgs field might be in a metastable state. So it's not actually at its ground state, but instead this kind of semi-stable state. But eventually what might happen is that there might be a point within the field anywhere in the universe in which it collapses into its ground state, and then that will be a nucleation event, which triggers the rest of the universe to follow suit, and that essentially destroys everything as a bubble travels outward from that site at the speed of light. It could be happening now if this were to be true, but just another kind of universe-ending thing to do with changing of states.
And I also want to point out that also entropy and time, to me, is they are very closely related. How do you define time? Even in GR, I assume time is a dimension, but like how do actually time progress? There have been theories since ancient philosophy. Think about time, right? It's like maybe the world's made of fire. It was Heraclitus, right? It's about change. The only way to measure time is to measure change. I mean, I don't think that's uncommon in science. It's like how you measure time. You have to measure some kind of change. The cesium atom at clock, you have to measure change. And but what is change? Why do things change, right? And what are things that change naturally? And to me, it's like, well, things change naturally to increase entropy. So the fact that we have this gradient of entropy actually maybe the consequence of changing entropy create out what we perceive as time. And to me, that's a strong thing to say. Like it's pretty. It's pretty extreme, like because we change entropy, and the fact that entropy changes create time, as the humans perceive it, right? So I think that's why entropy is not just a way of counting; it's a way that counting progress time. People that to reach a more state of more uncertainty or more chaos. Well, not chaos. I hate this word chaos. More disorder. But the fact that naturally a system wants to go to a system want to have a more disordered state that itself generate what we perceive as time.
Yeah, I always hear, like this asymmetry in the fact that entropy tends to increase when you don't put work in. That I've heard people talk about how that's the reason why you can't go backwards in time. But very interesting stuff, Pheely. If you ask any physicist what the most kind of fundamental truth is of nature, I think 99% of them would say the second law of thermodynamics, which is, entropy increases, but a lot of them don't truly understand it. So I thought I learned a lot today, actually, hearing what you had to say. But for the sake of time, I think we should move on, unless there's any last comments anyone wants to make.
Well, I'll just wrap up. Just a take-home message. The crux of this is that, well, there's something called entropy that can be a disorder, and things want to be the most disorder as possible. And the most disorder of the universe is not. We don't have Earth. We don't have planets. Right? The most disorder just plain nothing. It's like everything breaks down to whatever you call the most fundamental state. And that is the heat death of the universe. It turned up to be the most entropy possible, the maximum entropy. And there's nothing you can do inside the universe to change that. And it might take a very, very long time, infinite amount of time in human cognition. So that's the story of the heat death of the universe.
All right. Again, there are other theories. I just want to point that out for those people who might believe those or for other reasons. I don't know the details of them, so I can't say which is more correct than the other. I mean, heat death of the universe seems pretty reasonable to me. Like, you normally try to not anger the gods of entropy. So, anyway, Patrick, if people want to ask about this very interesting discussion, how do they do that?
Well, there are a couple different ways in which people can contact us to contribute their thoughts to the conversation or suggest future conversations. The first way is through our email account. We are hyperthesispodcast@gmail.com. We also have an Instagram at the Hyperthesis where you can follow us, you can DM us, and we'll post updates about when we post episodes, as well as some behind the scenes images and also some memes from our meme lord, Liam. You can also find us.
I never post memes ever. Like, very rarely do I post
You
memes.
should post
and you
more.
keep telling people I do. I have to start doing it. The problem is that I don't want to steal people's memes. I don't want to take credit for them, so I have to create my own, and that's a very slow process.
We might start seeing more original memes from Liam on our Instagram. Should he deign it to be beneath or worthy of his time. So you can find us on Instagram. You can also find us on YouTube. Just search Hyperthesis Podcast or the Hyperthesis Podcast. If you'd like to listen to us, which I assume you're doing right now, we can be found on YouTube. We have excellent animations as done by Pheely. And we also have all our episodes, which are also edited by Pheely, available on Apple Podcasts, Google Podcasts, Amazon Music, Spotify. We are hosted out of anchor.fm/the Hyperthesis. So you can find us wherever you get your podcasts. So feel free to like, rate, review, and suggest topics. Or if you would like to be on the show as a guest talking about your topic of expertise, let us know and we would love to have you on.
All right. So today we have a story from Patrick about the inside of the Earth, I guess, like you said at the beginning of the episode. So take it away.
Okay. So we've talked about the heat death of the universe and how things like to find their final states. But going back to the current age, we have something that is very hot, and that is beneath our feet. And so what I'm talking about is the layers underneath the Earth. So last week we talked about the layers of the atmosphere. So today I'm going to reverse course and deep dive into the Earth. Now, as we mentioned before, we can't actually dive into the Earth. The deepest borehole that we have is about 12 kilometers into the crust. And the crust is the top layer of the Earth's many, many different layers beneath. Now, these layers we don't really interact with on a daily basis, but we'll be getting into what each of them do, how each of them exist, and maybe a bit into how we can sense these different layers. But before getting to the hot stuff, let's talk about the crust. Now, the crust is the thinnest of all layers and contains everything that we experience. From the mountain ranges to very deep ocean trenches, the crust is an immense area covering the entire surface of the Earth, and it's relatively cool compared to the inner layers. So it's actually solid, we can walk on it, but we still see a lot of changes that lead to sometimes catastrophic events. So the crust overall is between 5 kilometers to 70 kilometers thick. So in areas where it's thinner, we might see more activity, such as volcanic activity, whereas the thicker places tend to be more stable, or where there are mountains or there's a lot of piling up. Now, based on the properties of the layers below, which we'll get into in just a second, the crust is always moving, and it rides along on currents produced below it. And the things that do the riding are known as plates or tectonic plates. Now, these tectonic plates, all pieced together, make up the surface of the Earth. And they contain mostly lighter elements like oxygen, silicon, or aluminum. And these lighter elements, when the Earth first formed, kind of floated to the top and formed the crust. So most of our crust is actually made out of oxides, mainly silicon oxide and aluminum oxide. Now, the plates that make up the crust move very slowly on human scales, and they average about 3 to 5 centimeters of movement per year. Now, sometimes that movement is stopped by another plate when they push up against each other, and this causes a lot of tension to build, almost like in a bow or in a rubber band as you stretch it. And it can release quite drastically, such as what we saw just happen recently in Turkey and Syria, where the Anatolian plate sprang, essentially, and released a bunch of tension that had been building up over time. And this caused it to shift into some places up to 5 meters. Just as a side note on that, I would encourage you, if you are able to help with the relief effort in Turkey and Syria. It's a massive disaster that went on, having a plate shift 5 meters in a split second. So there's a lot of aid that needs to be contributed to that. So if you're able, please do. Now, this ever-changing surface of the Earth is dictated by what's below the crust, which is the mantle. And that's the next layer in our journey to the center of the Earth. So at around 3,000 kilometers thick, the mantle is by far the largest layer, making up almost half of its radius. The Earth itself is about 6,000 kilometers in radius, maybe just a bit more. And it also consists mostly of iron, magnesium, and silicon, and of course other trace minerals as well. And these swirl around in a hawk-thick liquid, and sometimes not even quite a liquid, more like a very, very, very dense goo. Now this consistency ranges in coolness and viscosity. So close to the crust, the mantle is actually quite solid. And together with the crust, this solid layer forms what's known as the lithosphere, whereas deeper down it gets hotter, where it might have the consistency of a thick caramel sauce. So this very molten mess derives a lot of its heat from one of the outer cores, and this causes convection currents in which the crust can ride on, and we get tectonic plate movement from these convection currents. And now, within the mantle itself, the molten region doesn't actually start for another 100 to 200 kilometers beneath the surface. So there's this nice solid part that rides on top. Now, there are two cores to the Earth. There's the outer core and the inner core. Now, the outer core has very strong convection currents because it's a lot hotter. It's under a lot of pressure, and it's also powered by radioactive elements like uranium and thorium, which contribute heat as they decay. And this circulation that occurs from this very extreme temperatures causes electrical currents, since it's mostly composed of nickel and iron. And as these islands and currents of nickel and iron circulate, they create electrical currents, which then induce a magnetic current. And this magnetic current is what we see as the magnetic field of the Earth. And this magnetic field actually flips occasionally. So there's a lot of interesting things going on in the outer core that will cause it to flip periodically. So every couple 100,000 years, the outer core and the magnetic field produced by it will flip. So what becomes the North Pole is now the South Pole. And so we're seeing a lot of changes in the pole. So who knows, it might flip soon. However, this flip in polarity is something that we can look backward in time to see based on the orientation of magnetite in our rock and layers of rock. Now, this super hot outer core, which is powered by uranium and thorium, surrounds the inner core, which is about 1,200 kilometers in diameter, and it's the center of the Earth as a solid metal ball. Now, it's super hot, so you might think it would be liquid, and it's mostly iron and nickel. However, due to the very high pressure, it's actually a solid core. And this actually spins faster than the rest of the planet. So the Earth takes 24 hours to rotate, and this is a bit quicker than that. It is around 5,400 degrees Celsius here, so similar to the surface of the sun. And again, very high pressure and therefore temperature, which drives high temperature, especially in the outer core and surrounding layers. Now, there may even be an inner core to the inner core, which is composed just of essentially iron, but we're still not sure. We are trying to recreate these types of pressures and temperatures in a lab, and there is some success with this, but it's still an active area of research. And this area became so hot in the first place, and we have this nice layer separation because of the original formation of the Earth. So as rocks bashed into each other during the formation of the solar system, there was a lot of heat generated by this. And as there was a lot of heat, things became molten, and lighter elements floated to the top, heavier elements floated down towards the bottom. That's why we have a lot of uranium and thorium, and also iron and nickel in the cores, because those are heavier elements. Of course, they congregated towards the center. Now, this heat is still maintained because of nuclear reactions, and there's a lot of lasting heat and insulation from the initial collisions. And these collisions are a story for another time, including the possible collision of a whole planet with the Earth during its early days. However, regardless, if we journey into the center of the Earth, we don't find dinosaurs or anti-gravity chambers, and we most likely wouldn't build an elevator that goes straight through the core. However, it is still fascinating. It's fascinating how we study it. If you would like to discuss how we study it and be a guest on our show, let us know. But it's really interesting to know what's beneath us without ever having seen it or having any way to interact with it.
Well, thank you very much for that, Patrick. It's kind of mind blowing how little of our own Earth we have access to, like the inside of it, or even like the oceans, right? And we know so much about our universe in space, although there's still tons that we don't know. But anyway, that's it, everyone. Thanks for joining us for our 31st episode. That was a good one. It was a very thought-provoking one. We'll see you guys next time.
Take care.
Bye, everyone.